TE light wave, we shall discuss the reflection of TE light wave in this class and the reflection of light wave in the upcoming class. TE stands for transverse electric. So TE stands for transverse electric light wave. We will consider two media, medium number 1 and medium number 2. The light wave will travel from medium number 1 to medium number 2, and we shall assume that these two media are lossless media, so we shall not consider the attenuation of the light signal in medium number 1 as well as medium number 2. TE stands for transverse electric wave, and if the electric field intensity is normal to the direction of the propagation of the wave, or it is normal to the plane of propagation, then this wave is known as transverse electric wave, which is represented by TE. If the wave is TM wave, then the magnetic field intensity of this wave will be perpendicular to the plane of propagation. It will be perpendicular to the direction of propagation. So TM stands for transverse magnetic wave. Anyhow, in this particular class, we are going to talk about the reflection of the transverse electric wave, and we shall consider the electric field intensity of the incident wave, the electric field intensity of the reflected wave, the electric field intensity of the transmitted wave, and this electric field intensity will be normal to the plane of propagation. Why? Because when the electric field intensity is normal to the plane of propagation, then the wave is known as transverse electric wave. So we consider the electric field intensity of the light wave in a lossless medium, and the electric field intensity of the light wave in a lossless medium is given by equation number 1. The electric field intensity is equal to E naught e raised to power minus jkz. Ax is the unit vector, and this unit vector gives you the direction of this vector E, which is the electric field intensity. This minus sign indicates that the wave is traveling along positive z axis. So as the wave is traveling along positive z axis, we represent the propagation constant with the help of a vector quantity, and we consider this propagation vector in the direction of the motion of the wave, in the direction of the propagation of the wave. So as the wave is moving along z axis, we consider this vector in the direction of the unit vector az. So vector k is equal to k az. The unit vector az gives you the direction of the propagation of the light wave. And then we consider a three-dimensional distance vector that is represented by r. This is a three-dimensional vector. This three-dimensional distance vector has three components. Xax is the component along x-axis, YAY is the component along y-axis, and ZAZ is the component along z-axis. And what we do, we calculate the scalar product of these two vectors. The scalar product of these two vectors is equal to k dot r. So let us talk about, you see, the scalar product of vector k and vector r. So AZ dot AX results in 0. So the first component of k dot AR will be equal to 0. Why? Because AZ dot AX is 0. Similarly, AZ dot AY results in 0. So the second component of k dot R will be 0. Why? Because AZ dot AY is 0. And there will be only one component of k dot R. Why? Because AZ dot AZ results in 1 and k dot R will be equal to kz. So this is how we calculate the scalar product of these two vectors. The scalar product of these two vectors will result in kz. So let us go ahead to the next slide. You see, the scalar product of k dot r results in kz. Why? Because AZ dot AX 0, AZ dot AY results in 0, and AZ dot AZ results in 1. So SK dot R results in kz. So we consider equation number 1 and we replace kz in equation number 1 by k dot r. So we replace this kz in equation number 1 by k dot r. Why? Because k dot r results in kz. So we replace this kz in equation number 1 by k dot r. So let us replace this kz in equation number 1 by k dot r. So if we replace this kz in equation number 1 by k dot r, we get equation number 2. This is the electric field intensity of the light wave in a lossless dielectric medium. So the electric field intensity is equal to E naught into e raised to power minus jkr, and this unit vector gives you the direction of this vector quantity, the direction of the electric field intensity. So we can represent the electric field intensity of the light wave with the help of equation number 2, and equation number 2 gives you the electric field intensity of the light wave in a lossless medium. Definitely we shall assume that medium number 1 as well as medium number 2 is a lossless medium. We shall consider the figure in this diagram. You see, there are two media in this diagram. Here is medium number 1. So the permeability of medium number 1 is mu naught. The permittivity of medium number 1 is epsilon 1. And here is medium number 2. The permeability of medium number 2 is mu naught, and the permittivity of medium number 2 is epsilon 2. We consider the interface between medium number 1 and medium number 2. So here is the interface between medium number 1 and medium number 2. This is a plane boundary between medium number 1 and medium number 2. This plane boundary is located at z is equal to 0 plane. So this is z is equal to 0 plane. Z is equal to 0 plane in this particular diagram represents the boundary between medium number 1 and medium number 2. And we know that z is equal to 0 plane is also known as xy plane. So if it is xy plane, then x-axis will be tangential to this boundary, it will be tangential to this interface. If it is xy plane, then definitely y will be tangential to this boundary, y will be tangential to this interface as well. So as the boundary is located in the z is equal to 0 plane, so x-axis and y-axis will be tangential to this boundary, it will be tangential to the interface between medium number 1 and medium number 2. And z-axis, you see here is z-axis. Z-axis is normal to the interface. Z-axis is normal to the boundary. So the only coordinate which is normal to the boundary, which is normal to the interface, is your z coordinate. X coordinate is tangential to the interface. Y coordinate is tangential to the interface. So we consider the different wave in this particular diagram. You see, here is the incident wave. Here is the incident wave. The electric field intensity of the incident wave is represented by EI. The propagation constant of the incident wave is represented by K1. So K1 is represented with the help of a vector, and this vector is always considered in the direction of the propagation. And the incident wave makes an angle of theta I with respect to normal. You see, z-axis in this particular case is the normal to the interface. So the angle of incidence in this particular case is theta I. We consider the reflected wave now. So a fraction of the energy of the incident wave will be reflected from the interface, and this wave is known as reflected wave. So some energy of the incident wave will be reflected back to medium number 1, and this energy is represented with the help of reflected wave. So the electric field intensity of the reflected wave is represented by ER. So ER is the electric field intensity of the reflected wave. The propagation constant of the reflected wave is represented by K1 prime. This is a vector quantity, and the direction of this vector basically gives you the direction of the propagation of the reflected wave. And theta r is the angle of reflection with respect to this normal. So theta I is the angle of incidence, theta r is the angle of reflection. The remaining energy of the incident wave will be transmitted to the second medium, and this wave is known as transmitted wave. This energy is transmitted to the second medium. So the electric field intensity of the transmitted wave in this particular case is represented by E2. The propagation constant of the transmitted wave is represented by K2, and theta t is the angle of transmission. If you want to transmit the wave from medium number 1 to medium number 2, then we don't want this reflection wave at all, because the loss in the energy of the wave will take place. The energy of this incident wave will be lost due to the reflection process. So if you want to transmit the energy of the incident wave to the second medium, then the reflection process is an undesirable process. We need to eliminate this reflection process. We need to eliminate the reflected wave, because some energy of the incident wave will be lost due to this reflection phenomena. So reflection is a very important topic in the subject of fiber optic communication system. We shall discuss the importance of the reflection later on in the upcoming topics. So in this particular diagram, the incident wave is moving towards the interface, and the incident wave is making an angle of theta I with respect to normal. Here is your normal. Z-axis is normal to the interface. Z-axis is normal to the boundary between medium number 1 and medium number 2. Some energy of the incident wave will be reflected back to medium number 1, and the angle of reflection is represented by theta r, and the remaining energy will be transmitted to the second medium. We know that the angle of incidence will be equal to the angle of reflection. So in this particular diagram, the incident wave is moving towards the interface. A fraction of the energy of the incident wave will be reflected back to the same medium, and the remaining energy of the incident wave will be transmitted to the second medium. The angle of incidence will be equal to the angle of reflection. Now what we do, we resolve K1 into two components, we resolve K1 prime into two components, and we resolve K2 into two components. K1 is a two-dimensional vector, so we are going to resolve K1 into two components. Similarly, K1 prime is a two-dimensional vector. We resolve K1 prime into two components. K2 is a two-dimensional vector as well. We are going to resolve all these three vectors into two components. So let us resolve the first component, the first vector K1 into two components. So we consider the vector K1 in this particular diagram, and we know that the angle of K1 with respect to the normal is theta I. We resolve K1 into two components. We get K1 sine theta I, which is the y component of this vector, and we get minus K1 cos theta Az, which is the z component of this vector K1. So we resolve K1 into two components with the help of this particular diagram. This is the component which is along y-axis, and this is the component which is along negative z-axis. So we resolve K1 into two components, K1 sine theta I Ay minus K1 cos theta I Az. So K1 is equal to K1 sine theta I Ay minus K1 cos theta I Az. Now we replace K1 sine theta I by K1y, because this is the magnitude of the component which is along y-axis, and we replace K1 cos theta I by K1z. Why? Because this is the magnitude of the component which is along z-axis. So we replace K1 sine theta I by K1y, and we replace K1 cos theta I by K1z. So if we replace K1 sine theta I by K1y and K1 cos theta I by K1z, so K1 will be equal to K1y Ay, excuse me, K1y Ay minus K1z Az, right? So this is the vector K1. Vector K1 has been resolved into two components, K1y Ay minus K1z Az. And what we do, we consider the three-dimensional vector R, which has a component along x-axis, which has a component along y-axis, and which has a component along z-axis. We have already considered this three-dimensional distance vector. So we take the scalar product of these two vectors, we take the scalar product of k1 and the scalar product of this vector r. You see, if we take the scalar product of these two vectors, so the scalar product of these two vectors results in k1 y minus k1 z. So equation number 3 gives you the scalar product of these two vectors, that is k1 dot r. That is the scalar product of k1 and vector r. So k1 dot r will be equal to k1 y minus k1 z. Now what we do, we consider k1 prime in this diagram. So here is k1 prime in this diagram, and we know that theta r, the angle of reflection, is equal to the angle of incidence. The angle of reflection will be equal to the angle of incidence. So this angle is replaced by theta I, and we resolve k1 into k1 prime into two components. You see, this is the component which is along y-axis, and here is the component which is along z-axis. So the component of this vector which is along y-axis is k1 sin theta I ay, and the component of this vector which is along z-axis is k1 cos theta I az. So in this particular diagram, we have resolved k1 prime into two components. K1 prime will be equal to k1 sin theta I ay plus k1 cos theta I az, and we know that we replace k1 sin theta I by k1 y, and we replace k1 cos theta I by k1 z. So this vector k1 prime will be equal to k1 y ay plus k1 z az. So we have resolved k1 prime into two components as well. Now let us resolve k2 into two components. Well, before before making discussion on the two components of k2, let us consider k1 once again. So we consider k1 once again. This is the vector k1 prime, which has got two components. Here is the component which is along y-axis, and here is the component which is along z-axis. And we know that we considered a three-dimensional vector r, and this three-dimensional vector has three components: the component along x-axis, the component along y-axis, and the component along z-axis. So we considered a three-dimensional distance vector r, and what we do, we take the scalar product of k1 prime and this vector r. So if we take the scalar product of these two vectors, k1 dot r will result in k1 y plus k1 z. So the scalar product of k1 and r results in k1 y plus k1 z. This is the value of k1 prime dot r. So now we consider k2, and we resolve k2 into two components. We know the angle of k2 with respect to the normal is theta t, which is the angle of transmission. So we resolve k2 into two components. Here is the component of k2 which is along the y-axis, and here is the component of k2 which is along z-axis, which is along negative z-axis. So k2 has been resolved into two components. The component of k2 which is along y-axis is k2 sin theta ay, and the component of K2, which is along negative z axis, is minus K2 cos theta t. So we can write down K2 in this particular form. K2 will be equal to K2 sin theta t ay minus K2 cos theta t az. And we replace K2 sin theta t by K2y and K2 cos theta t by K2z. So K2 will be equal to K2y ay minus K2z az. So this vector K2 has been resolved into two components, and K2 is equal to K2y ay minus K2z az. And we are going to show that K2y is basically equal to K1y. So you see, instead of K2y, you guys have K1y over here. So we can show that K2y is equal to K1y. So we are going to consider the Snell's law of reflection, and we are going to show that K2y will be equal to K1y. So we will consider K1y in equation number 5 instead of K2y. So let us consider the Snell's law, and let us show that K2y is equal to K1y. So we consider the Snell's law of reflection. According to Snell's law of reflection, n1 sin theta I is equal to n2 sin theta t. In other words, K1 sin theta I will be equal to K2 sin theta t. So K1 sin theta I is equal to K1y, and K2 sin theta t is equal to K2y. And we have shown that according to Snell's law of reflection, K1y is equal to K2y. So you guys can replace K2y by K1y. All right. So let us consider the scalar product of K2 and R. You know, vector R has three components. It has a component along x-axis, it has a component along y-axis, and it has a component along z-axis. So the scalar product of K2 and this three-dimensional distance vector R will give you K1yy minus K2zz. Now we consider medium number 1. Let me consider medium number 1 in the diagram. If you consider medium number 1 in the diagram, there are two waves in medium number 1. There are two waves in medium number 1. We have the incident wave and we have the reflected wave. So we will consider the electric field intensity of the incident wave, which is medium number 1, and we will consider the electric field intensity of the reflected wave, which is in medium number 1 as well. The only wave which is in medium number 2 is the transmitted wave. So we consider medium number 1, and there are two waves in medium number 1, the incident wave and the reflected wave. We are going to consider the electric field intensity of the incident wave and the electric field intensity of the reflected wave, and we will consider the electric field intensity of the transmitted wave in the second medium. So we consider medium number 1, and you see there are two light waves in medium number 1, the incident wave and the reflected wave. So we consider medium number 1 and we consider the incident wave in medium number 1. So the electric field intensity of the incident wave will be equal to E naught into e raised to power minus j k1 dot r. We know that the propagation constant of the incident wave is k1 dot the propagation constant of the incident wave is k1, and we have already simplified k1 dot r, right? So what we do, we put the value of k1 dot r in equation number 7, and if you guys remember, k1 dot r is equal to k1 y minus k1 z z. So we put this value of k1 dot r in equation number 7. So let us put this value in equation number 7. So the electric field intensity of the incident wave will be equal to E naught into e raised to power minus jk1 y plus jk1 z, and this vector is along x-axis, and this is equation number 8. So we put the value of k1 dot r in equation number 7, and we consider equation number 8. Now we consider the reflected wave in medium number 1. So we know that a fraction of the energy of the incident wave will be reflected back to medium number 1, and this energy is represented by reflected wave. So the electric field intensity of the reflected wave will be equal to rho E naught into e raised to power minus j k1 prime dot r. We know that the propagation constant of the reflected wave is k1 prime. That's why we consider k1 prime over here. So rho is known as the reflection coefficient, and rho E naught gives you the fraction of the amplitude of the incident wave, is the fraction of the amplitude of the incident wave which is reflected back to medium number 1. If 100% energy of the reflected wave of the incident wave is reflected back to medium number 1, then rho will be equal to 1. So if rho is 1, then the total energy of the incident wave will be reflected back to medium number 1. So rho E naught basically represents the fraction of the amplitude of the incident wave which is reflected back to medium number 1. So rho is known as the reflection coefficient. We will focus on the reflection coefficient. We will focus on this rho. Rho plays a very important role in the fiber optic communication system as well as in the wireless communication system. So we will find out the equation for rho. So what we do, we put the value of k1 dot r, and we know that the value of k1 dot r is we have k1 yy plus k1 z. So this is the value of k1 prime dot r. So if we put this value of k1 prime dot r in equation number 9, we obtain equation number 10. So the electric field intensity of the reflected wave in equation number 10 is equal to rho E naught into e raised to power minus j k1 yy minus j k1 zz, and definitely the reflected wave will be in the direction of the unit vector ax. So you see, there are two waves of the same frequency in medium number 1. There is an incident wave and there is a reflected wave, and as the frequency of the incident wave and the reflected wave remains the same, so the interference of these two waves will take place. So the total electric field intensity in medium number 1 due to this interference will be equal to E1. So E1 represents the total electric field intensity in medium number 1, and the total electric field intensity in medium number 1 will be equal to the phasor sum of the electric field intensity of the incident wave and the electric field intensity of the reflected wave. So the phasor sum of the electric field intensity of the incident wave and the reflected wave will give you the total electric field intensity in medium number 1. So what we do, we put the values on the right hand side of this particular equation. So if we put the value on the right hand side of this particular equation, we obtain equation number 11. This is equation number 11. So the total electric field intensity in medium number 1 will be equal to E naught into e raised to power minus j k1 yy plus j k1 zz plus rho E naught into e raised to power minus j k1 yy minus j k1 zz, and the direction of this vector is given by this unit vector ax. So equation number 11 gives you the total electric field intensity in medium number 1. We have discussed the electric field intensity in medium number 1, and you see the electric field intensity, total electric field intensity in medium number 1 is along x-axis, which is tangential to the interface. If you guys remember, ax, we discussed that the unit vector ax and the unit vector ai are tangential to the interface. These two unit vectors are parallel to the interface, and the unit vector az is normal to the interface. So the only unit vector which is normal to the interface is az. The remaining two unit vectors, I mean ax and ay, are tangential to the interface. So the total electric field intensity in medium number 1 is parallel to the interface. Why? Because it is along x-axis. Now we consider medium number 2, and there is only one wave in medium number 2, that is the transmitted wave. So when the incident wave travels from medium number 1 to medium number 2, at the plane boundary, a fraction of the energy of the incident wave is reflected back, and the remaining energy of the incident wave is transmitted to the second medium. So we consider the electric field intensity of the transmitted wave in the second medium. The phasor value of the electric field intensity in the second medium is represented by E2, and tau E naught represents the fraction or the remaining energy of the incident wave which is transmitted to the second medium. If the amplitude of this medium is E naught, then tau will be equal to 1, and it means that the total energy of the incident wave will be transmitted to the second medium. If tau is equal to 1, there will be no reflection in this particular case. If tau is equal to 1, then there will be no reflection in this particular case. The total energy will be transmitted to the second medium. So tau E naught represents the portion of the amplitude of the electric field intensity which is transmitted to the second medium. So E2 is equal to tau E naught into e raised to power minus j k2 dot r. We know that the propagation constant in the second medium is k2, and we put the value of k2 dot r in equation number 12. And if you guys remember, this k2 dot r was equal to k1 y minus k2 z. So we put this value in equation number 12. If we put this value in equation number 12, equation number 12 can be written as, so equation number 2 can be written as, because we put the values of k2 dot r in equation number 11, and we obtain equation number 13. So E2 will be equal to tau E naught into e raised to power minus j k1 yy plus j k2 zz multiplied by ax. So this is the electric field intensity of the transmitted wave which is in medium number 2. And you see the electric field intensity of the transmitted wave is along x-axis. So E2 is entirely tangential to the interface as well. There is no component of E2 which is normal to the interface. There is no component which is along Z axis. So now we are going to talk about the boundary conditions. Well, rho in this particular topic is known as reflection coefficient, and tau in this particular case or in this particular topic is known as transmission coefficient. So we talk about the boundary conditions. The boundary condition states that whenever a wave travels from one medium to another medium, the tangential component of the wave does not change. However, its normal component changes. So whenever a wave travels from one medium to another medium, the tangential component of the wave will not change and the normal component of the wave will change. So in our case, the wave E1 is moving towards the wave E1 is moving towards the wave E1 is moving towards the second medium. E1 is traveling from medium number 1 to medium number 2. And E1 is the total electric field intensity of this wave in medium number 1, while E2 is the total electric field intensity of this wave in medium number 2. So this condition, this boundary condition states that the tangential component of E1 in medium number 1 will be equal to the tangential component of E2 in medium number 2, and we already know that E1 is entirely tangential to E1 and E2 is entirely tangential to E1 is entirely tangential to the interface and E2 is entirely tangential to the interface. So as E1 is entirely tangential to the interface and E2 is entirely tangential to the interface as well, so according to the boundary condition, the tangential component of E1 will be equal to the tangential component of E2. There is no normal component of E1, there is no normal component of E2. So E1 will be equal to E2, and we know that E1 is in terms of Z, E2 is in terms of Z as well, and this equation will be valid at Z is equal to 0. So what you guys can do, put the value of Z in in E1, put Z is equal to 0 in E1, and then put Z is equal to 0 in E2 and simplify this equation. The simplification of this equation will gives you 1 plus rho, which is equal to tau. So E1 will be equal to E2, put the value of Z in E1 and put the value of Z in E2 and then simplify this equation, and the simplification of this equation results in this particular equation, which is 1 plus rho, and 1 plus rho is equal to tau. Now what we are going to do, we are going to find out the total magnetic field intensity in medium number 1, and we are going to find out the total magnetic field intensity in medium number 2. So let us find out H1, the total magnetic field intensity of the wave in medium number 1, and let us find out H2, which is the total magnetic field intensity of the wave in medium number 2. And we know that H1 travels from medium number 1 to H2, and the tangential component of H1 in medium number 1 will be equal to the tangential component of H2. Why? Because this is the boundary condition, and the boundary condition states that whenever a wave travels from one medium to another medium, the normal component of the wave changes, but the tangential component of the wave does not change. So we will compare the tangential component of H1 to H2, because the tangential component of H1 will be equal to the tangential component of H2. So let us establish the equation for H1 in medium number 1, and let us establish the equation for H2 in medium number 2. So we establish the equation for H1 in medium number 1 with the help of Maxwell equation. You see, this is one of the 4 equations of Maxwell which states that curl of the electric field intensity will be equal to minus j omega b, and we know that b is equal to mu h. So the curl of the electric field intensity will be equal to minus j omega mu h. We know that in medium number 1 h will be h1 and e will be e1. So we calculate h1 with the help of this particular equation. H1 is the total magnetic field intensity of the wave in medium number 1. So the second last equation will give you H1 in medium number 1. So H1 will be equal to 1 over minus j omega mu naught, and then we have the curl of the electric field intensity in medium number 1, and the electric field intensity in medium number 1 is E1. So we can calculate the total magnetic field intensity in medium number 1 with the help of equation number 14. So let us simplify the right hand side of equation number 14, and you see H1 will have two components. One component of H1 will be tangential to the interface, the other component of H1 will be normal to the interface. We are not interested in the normal component, because whenever the wave travels from one medium to another medium, the normal component of the wave changes. So we shall focus the tangential component of H1. So let us simplify the right hand side of H1. So we go to the next slide, and we simplify the right hand side of H1. So H1 is equal to 1 over minus j omega mu naught, and as far as the curl of the electric field intensity E1 is concerned, we calculate the curl of this E1 with the help of this determinant. So what do we have? We have AX in the first row, AY in the first row, and AZ in the first row. Then we have curly y curly x, curly y curly y, curly y curly z in the second row. We consider the third row of this determinant. So here is the x component of E1, and here is the y component of E1, and here is the z component of E1. So let us consider E1, and you guys will see that E1 has only one component, that is the x component. E1 has no component along y axis and no component along z axis. So I am going to consider the equation for E1 in order to show you guys that there is only one component of this vector E1, that is the x component. The y component of E1 is 0, and the z component of this E1 is 0, and then we will come towards the expansion of this determinant. So let us consider the equation for E1. We consider the equation for E1. Here is the equation for E1. So we consider the equation for E1. Here is the equation for E1, and you see E1 is in the direction of the unit vector AX. There is no component in the direction of the unit vector AY. There is no component in the direction of the unit vector AZ. So this is the x component of this vector. The y component of this vector is 0, and the z component of this vector is 0 as well. Excuse me. So E1 has only one component, which is the x component. So let us go back to this determinant. We calculate H1. So you see there is only one component of E1. So here is the x component of E1. So the x component of E1 is E naught into e raised to power minus j k1 yy plus j k1 z plus rho E naught into e raised to power minus j k1 yy minus j k1 zz. The y component of E1 is 0 and the z component of this is, you see, az. So the z component of E1 is 0 as well. So what we do, we expand this determinant. So the expansion of this determinant will give you two components. So you see, if we expand the determinant on the previous slide, we get two components. One component of H1 is in the direction of the unit vector AY, which is tangential to the interface, and the second component of this H1 will be in the direction of AZ, which is normal to the interface. We are not interested in this normal component. We are interested in the tangential component of H1 only. So let us consider this tangential component only. So we expand the determinant on the previous page, and H1 is a two-dimensional vector, and this vector has a component along y-axis, another component along z-axis. The component along y-axis will be tangential to the interface. The component along z-axis will be normal to the interface. We are not interested in the normal component at all. So let us consider the tangential component of H1. So we consider the tangential component of H1. The tangential component of H1 is equal to 1 over minus omega mu naught k1z E naught into e raised to power minus j k1 yy plus j k1 zz minus k1z rho E naught e raised to power minus j k1 yy minus j k1 zz, and you see this component is along y-axis, which is tangential to the interface. So we have calculated the tangential component of H1. Let us calculate the tangential component of H2. H2 will be in medium number 2. H2 is the magnetic field intensity of this wave in medium number 2. So we can calculate H2 with the help of this particular equation. H2 will be equal to 1 over minus j omega mu naught, and then we have the curl of the electric field intensity E2, and the curl of the electric field intensity E2 can be calculated with the help of a determinant, which is on the next slide. So the determinant on the next slide will give you the curl of this electric field intensity E2. So let us simplify the right hand side of this last equation. So we simplify the right hand side of this last equation. So H2 is equal to 1 over minus j omega mu naught, and this determinant is for the curl of the electric field intensity E2. So we have the unit vector AX, the unit vector AY, the unit vector AZ in the first row. We have curly by curly X, curly by curly Y, curly by curly Z in the second row. Then we have the X component of E2. We have the Y component of E2, and we have the Z component of E2. If you guys remember, E2 was along the unit vector AX. There was no component along the unit vector AY. There was no component along the unit vector AZ. So this vector E2 has only one component, which is in the direction of the unit vector AX. There was no component along y-axis. There was no component along z-axis. So the component of E2 was along x-axis only, and this component was tau E naught into e raised to power minus j k1 yy plus j k2 zz. This is the x component of E2. We expand this determinant. The expansion of this determinant will result in two components of H2. So we will obtain two components of this vector. One component will be in the direction of the unit vector AY, and another component will be in the direction of the unit vector AZ. we know that AY is tangential to the interface while AZ is normal to the interface. We are interested in the tangential component only. We are not interested in the normal component. So let us expand this determinant. The expansion of this determinant will give you two components, the component along y-axis and the component along z-axis. So if we expand the determinant on the right hand side of the previous equation, we get two components of H2. You see, here is the component which is along y-axis. This component is tangential to the interface, and then there will be another component in the direction of AZ, and this component is normal to the interface. We are not interested in the normal component. That's why we don't consider the details of the normal component in this particular case. So what we do, we consider the tangential component of H2 only, and we consider the tangential component of H2 in equation number 16. So equation number 16 gives you the tangential component of H2. So the tangential component of H2 will be equal to 1 over minus omega mu naught K2Z, then we have tau E naught into e raised to power minus j K1YY plus j K2ZZ, and this component is along the unit vector AY, which is tangential to the interface. So we have considered the tangential component of H1, and we have considered the tangential component of H2, and now we consider the boundary conditions. The boundary condition says that whenever a wave travels from one medium to another medium, the tangential component of the wave does not change. The normal component of the wave does change. So the tangential component of H1 according to the boundary condition will be equal to the tangential component of H2. Why? Because the tangential component does not change. So the tangential component of H1 in medium number 1 will be equal to the tangential component of H2 in medium number 2 near the interface. And the interface is located at z is equal to 0. So according to the boundary condition, HT1 will be equal to HT2. What is HT1? HT1 is the tangential component of H1, and HT2 is the tangential component of H2. And we know that HT1 and HT2 are in terms of z. So we put the value of z is equal to 0 in this particular equation. So you guys are requested to put the value of z is equal to 0 in HT1 and the value of z is equal to 0 in HT2. Then simplify this equation. The simplification of this equation will give you equation number 17. So K1z minus rho K1z will be equal to tau K2z. So if we simplify this equation, we obtain equation number 17. And we know that the coefficient of transmission is equal to 1 plus rho. So what we do, we put the value of tau in equation number 17. So if we put the value of tau in equation number 17, we obtain equation number this equation number. So let us put the values of tau on the right hand side. So we have K1z minus rho K1z. We put the value of tau on the right hand side. So we get K1z plus rho K1z, and we simplify this equation for rho. So the reflection coefficient can be calculated with the help of equation number 18. The reflection coefficient will be equal to K1z minus K2z, K1z plus K2z. And we know that K1z is K1 cos theta I and K2z is K2 cos theta t. So the reflection coefficient in this particular case will be equal to K1 cos theta I minus K2 cos theta t, K1 cos theta I plus K2 cos theta t. So we consider this equation for normal incidence now. You see, we consider the normal incidence now, and we will expand this equation later on in the second class as well. So let us consider equation number 9, and let us consider equation number 19. This is the equation for the reflection coefficient. Reflection coefficient is a very important quantity. I will talk about the importance of this reflection coefficient in a while. So what we do now, we consider the normal incidence. So we consider the normal incidence over here. We consider the normal incidence. We will talk about, you see, the normal incidence later on. Just focus on this particular equation number 19. We will explain this equation number 19 for the normal incidence and for the oblique incidence later on.